The first speaker in this session is Christian Traeger.
My presentation is pretty much a little back-of-the-envelope calculation, how important a more comprehensive treatment of uncertainty is for climate change and for mitigation policies. And we have talked quite a bit about ambiguity. That will actually be the very last part of the talk because I don't have any numbers. So I'd rather first go and point something else out, which is actually not for an ambiguous situation, but for a simple risk situation where we have probabilities and where pretty much all of the models that currently deal with impact assessment still don't take a comprehensive account of aversion to this uncertainty, to this risk. And I'll do that all via the social discount rate. So let me first give you an intuition. What is the social discount rate? Basically, it is a convenient tool for capturing the time development of consumption value. How much is the value of a unit of consumption today as opposed to in 50, 100 years? And that will determine how willing we are to do something about the future. And why is it actually really important in the climate context? Well, I'll take an illustration by Nordhaus in his open source dynamic integrated climate economy model. He ran the exact same model with two different discount rates. One is the discount rate that he advertises as a prescriptively correct discount rate of 5.5%. And if he runs the model with this discount rate, he actually finds that we should cut back the emission rate by 14% in the first commitment period, and the optimal carbon tax should be $35 per ton of carbon. And then he reruns the exact same model, only changing the social discount rate to the value that actually Nicholas Stern and his team used in the Stern review that they prepared on behalf of the British government, where they actually used a discount rate that came down to 1.4%. And the exact same model otherwise in terms of climate and everything gives you that we should cut back the emission rate by 53% in the first commitment period, and the optimal tax on a ton of carbon should be $360. So it looks like the discount rate seems to be pretty important. Obviously, most of the effects happen in the far future, so how we value our future is important. But here it's captured in the social discount rate. And yeah, then I want to introduce you to that other extension of uncertainty aversion, or risk aversion, actually, that except for actually one paper by Min hasn't been addressed at all in the debate on the social discount rate and the mitigation. That is something I call intertemporal risk aversion. It's very closely related to Epstein and Zinn's disentanglement of arrow-Pratt risk aversion from intertemporal substitutability. I want to motivate it differently here, though, with a little axiom. And what we need is two consumption paths. And let us not yet think about climate, about something much simpler here, 4 periods. And everybody of you can think of a nice situation and a bad situation. It could be like the mood of your coworker or the talks in the conference. So first you have a good mood of your coworker, for example, a bad mood. In the second period, good mood, bad mood. And X prime, the consumption path, differs that it starts out with a bad situation, gives you then the good situation, bad situation, good situation. Otherwise, they are pretty much the same. And yeah, preferences are denoted in the standard way. So what I need to define my axiom is we need one path that for any comparison like this, X high would be a consumption path that for every period collects the better outcome. And X low would be the consumption path that for every period collects the worst outcome here. So in our example, X high would be good mood of your coworker in every period, and bad mood would be X low. X low would be bad mood of your coworker in every period. So the axiom I want to ask you first has something that you have to buy. Assume you are indifferent between these two consumption paths. And some of you might raise the point that they actually discount the future positively. So they might not be indifferent between the two. They actually, for example, rather have you start out in a good mood because you more care about what is happening right now. So you might prefer the first consumption path here, which starts out better. And if that is the case, you can actually barely see it. But this guy is red now. And you can make this guy a little bit happier so that you feel indifferent between the two. Do that in your mind. Should be indifferent between these two consumption paths. And then I want to ask you this following little experiment here. Compare these two consumption paths, which is a lottery actually, So on the left-hand side, you can choose that your coworker is in a good mood state, bad mood state, good mood, bad mood in these 4 periods. On the right-hand side, you have a lottery, objective lottery. You toss a coin, probability a half, probability a half. And if tail comes up, you get a coworker who is in a good mood like all the 4 periods. If the other thing, what I didn't mention, I don't know, came up, you have a bad mood state of your coworker all the 4 periods. And I want to ask you basically who would be indifferent between these 2 situations? Who would prefer the certain outcome where he knows, like, every other time he's in a good mood at least, or who actually prefers a lottery where the coworker might be in a bad mood for all the time that you write this paper with him, or he might be in a good mood with equal probability for all the time. And let me ask you, actually, who has a preference? Who is indifferent? David is indifferent. Who might prefer the certain consumption path? Actually, quite a couple. That is nice. So, and who would prefer the lottery? No one. OK. Yeah, we have. OK, Rick. All right, all right. So it turns out that the only thing the standard model can actually do is it can describe indifference. So we had David, actually the only non-economist here who is described well by the model. But that might probably give me to think, because so far I only presented among economists, I guess. But OK, so if we want to present the sign that most of you actually figure to be their preference, we need something a little bit more general than the standard model. And sorry, the standard model, if I talk about the standard model, I simply mean that you additively aggregate over time and additively aggregate over uncertainty. So the way, I mentioned the literature it relates to on the way, I hope. So the way you can actually represent it is simply with an additional function that gives additional curvature while you're aggregating over uncertainty. And it's really closely related to what Sujoy presented yesterday, only that yesterday this additional curvature did set in when you actually had ambiguity. Here we only talk about uncertainty, and it turns out all the standard axioms for Neumann-Morgenstern, everything is satisfied here. It's kind of the model by Krebs and Porteus in '78, if you know this. And Epstein and Zinn made a similar point in disentangling intertemporal aspects from standard arrow-Pratt risk aversion in a paper early in the 90s for a special case, one commodity model with homothetic preferences. So if we want to be slightly more comprising in capturing uncertainty or risk attitude, then we want to put this function as a nonlinear function in there, especially as a concave function, if we want to capture the aversion to this intertemporal lottery setting. And now you can actually see that, or you would only capture your intertemporal trading of consumption over time, and F would actually capture this idea of risk as it was expressed in the axiom. And you can also calculate kind of the standard risk measure for this function F, which I would then call the relative intertemporal risk aversion coefficient, similar to the relative arrow-Pratt risk aversion in the atemporal setting. And if we actually go to the one commodity special case, that is the model that Epstein and Zinn, and at the same time Weil developed around 90, where they have just a homothetic function for a one commodity setting. And they have an infinite time horizon, and I stick here to this very simple 1.5 period model that has been used quite a bit in debating about the social discount rate and the optimal mitigation around climate change. So that's how it looks in the climate change debate, basically, setting. And the measure of relative intertemporal risk aversion simply is some mixture of my aversion to intertemporal substitution, trading consumption between different periods over time, and to risk aversion, where I actually aggregate over flips of coins. And where I want to get, one more remark here. Why I go to this very simple setting of Epstein and Zinn, because many people actually wreck their brains how to estimate this model, and it turns out to be a little bit more difficult than many standard estimations. And so there is a wide variety of results, unfortunately. And I think so Campbell, first Epstein and Zinn did it themselves. Then kind of Campbell tried to improve a little bit on that model. Wissing-Jurgensen used the Campbell model, tried to improve it further. But there are a lot of assumptions that you have to put in, and then depending on these assumptions, you actually get different results. So right here, I want to go with the best guess that Wissing, Jurgensen, and Attanasio derived for the Epstein-Zinn specification of the model, which is that the intertemporal elasticity of substitution, that is, it's high if you're actually willing to just like save something today and eat it tomorrow instead. It's very low if you actually want to have a very smooth consumption path over time. So they estimate this guy to be about 1.5. And the standard relative error Pratt aversion would be about 9.5. So that is like the point estimate. If I have time, I play around with the values. And if you calculate this coefficient of relative intertemporal risk aversion from there, it would be 26.5. Now, the little two-period thinking about the climate change model is extremely simple. You just have a present certain consumption, x1, and you have an uncertain future consumption, x2. And the two are related by a stochastic growth rate, which we assume to be normally distributed. And yeah, we assume that the expected value here of the growth rate is mu, and the variance is sigma. And the question that I want to ask is how much additional certain consumption in the future is welfare equivalent to an additional certain unit of consumption today. So basically, it's what are we willing to do today about having a little bit or being a little bit better off in the future. And the answer is simply this risk-free social discount rate. If we talk about risk-free transfers, I make a comment on that later on. And the answer is given by the, I think most of you are familiar with the Ramsey formula, where in the Ramsey would actually be the market rate of interest here. In the climate change debate, it's generally R is the social rate of discount, and you just look at the constituents, and the constituents of it are the pure rate of time preference, that is how you kind of intrinsically devalue the future. And then eta is the consumption elasticity of marginal utility, which is the inverse of your willingness to substitute over time, or your aversion to intertemporal fluctuations. So aversion to intertemporal fluctuations times the growth rate, or the expected growth rate, mu here. In the stochastic extension, you get an adaptation, or you get an additional term which takes account of the uncertainty that you face. So if you have a high variance, it actually becomes a little bit smaller, proportional to the variance, and also proportional to your aversion to intertemporal fluctuations. Now, getting back to the current debate that we had actually over the last 2 years, 3 years, Stern comes from a normative perspective and says, well, if we think about society as a whole, we shouldn't have a pure rate of time preference pretty much at all. He says, OK, basically, things converge better if you have 0.1. I mean, the point he makes is that we actually have a certain probability of dying, which you can one by one translate into, or getting extinct, society getting extinct. You can translate it one-to-one into a preference, pure preference of time. And then he says that our elasticity, or aversion to intertemporal substitution is 1, and the growth rate is probably 1.3%. While on the other hand, Nordhaus, who claims to have a descriptive approach, says that the pure rate of time preference is about 1.5%. The aversion to intertemporal substitution is 2, and the growth rate in his model comes out to be also approximately 2%. So he ends up with this value as opposed to the other value, which gave you this magnitude of 10, order of 10 difference in the carbon tax that I showed you on the first slide. Now, what happens if we actually put in a little bit of risk here in the standard model, and we say that the volatility per year is approximately 2%? It turns actually out that it's completely negligible. And it has been, in most of the discussion, it has been, what is the subset? I don't know. It has not been mentioned, basically. They haven't been talking about the last term, except for Weizmann, which I relate to afterwards. But there is the reason why. I mean, it really has very, very little effect if we are in the standard world here, where we assume everything would be normal, no fat tails, and we have just like a 2% volatility every year. Now, what happens if I add this idea of us being actually intertemporally risk averse? Oh, sorry. one more thing, without actually putting or assuming more values. And you can actually simply see that the variance here, if it's in the order of %, it makes this guy as the square of a unit order value and the square of the % order value 10 to 100 times smaller than the other terms in this equation, which really makes it negligible. So if you put in intertemporal risk aversion, you get this additional term, which always subtracts from the social discount rate, proportional to this coefficient of relative intertemporal risk aversion. And if we take the estimates by Wissing, Jurgensen, and Attanasio of eta equals to 2/3 and RRA 9.5, we actually find that the additional term is, so the upper, the numerator here is the intertemporal risk aversion term, and that was the only term that we had before. So the difference is 33, which kind of brings us back into the right order of magnitude, that uncertainty starts becoming important. If we throw in more values here, that is, we again assume Nordhaus's prescriptive values of 1.5 for the pure rate of time preference, expected growth rate of 2%, volatility of 2%, then it turns out to be still small, but it starts to play a role. The more interesting effect, however, is that because we disentangle between risk aversion and intertemporal substitutability, we now have a much smaller eta. Eta is 2/3 now, rather than it used to be 2. So the largest effect actually comes that this guy here, the growth term, the second term, now is only 1.3%, which was huge in the model of Nordhaus. So overall, we get a 2.5% discount rate rather than a 5.5% discount rate. And we still have a descriptive approach where we looked at the asset market data that Wissing, Jurgensen, and Attanasio estimated and plug it into this simplified two-period model. I think I have the values here, yeah. So the biggest effect stems from having eta being the aversion to intertemporal fluctuations being much smaller, which makes the growth effect quite a bit lower. And then there is an additional effect from intertemporal risk aversion. If, however, we think that the climate problem increases risks significantly beyond this yearly 2%, which might be IID currently, which might not be IID anymore if we have climate change, and if we think about a very, very simple approach, again, to this problem and say we keep the two-period model and we just look at 50 years, for example, we say keeping the expected growth rate of 2%, that we might, in expectation, be 2.7% wealthier than today. And then we assume some somewhat arbitrary climate change adjusted probability distribution. And I should come up with something better here. But just to play a little bit with some numbers, I chose that distribution or that variance here because it gives you a super small probability that in 50 years it could happen. Because of climate change, we would be worse off than today. So we saw some of the catastrophic scenarios yesterday that might actually make lots of us a lot worse off. And here it would actually be 0.04%, that is 0.0004. So it's pretty small that actually we really will be worse off. And still, as soon as you increase the probability accordingly, you actually find that this additional term, which comes from intertemporal risk aversion, eats up the growth term. And all you're left with is simply the pure rate of time preference, which, yeah, we kind of disagree about what it should be. But that is just an intuition why this aspect of risk aversion that is neglected in the current models might be pretty important. And also I want, OK, I skip, yeah, that is a sensitivity analysis. I skipped that one, actually. Just want to make the relation to what we were talking about yesterday, the model by Sujoy. Actually has a very similar result in this simple 1.5 period model. And we talked about this expression. Let me just remind you. If you have additional, like you have first order uncertainty here, which would, in my language, be a probability distribution pi that depends on some parameter theta. But the dark blue one is just the standard expected utility model. Now, Theta is unknown to us, so we have a prior over theta. That was the second order uncertainty here. And if we introduce this Bayesian prior and we equip it with this ambiguity aversion function that Sujoy introduced yesterday, which is the phi, basically meaning we additionally punish our second order uncertainty, then you get a very similar setting. We have one more probability distribution. So again, I assume it is normal. So our growth rate now is expected value theta, variance sigma square. And the expected value theta is in expectation what we had before, the mu, and has the additional variance tau. So instead of having one probability distribution, I have two. One would be kind of objective, or depending on a parameter, it would be objective. But we don't know that parameter. It's kind of this in the Bayesian prior. And the ambiguity function I choose is the constant relative ambiguity function. Again, you can define the coefficient of relative ambiguity aversion in the standard way. And you end up with exactly the same expression, only that intertemporal risk aversion now is replaced by relative ambiguity aversion. And yeah, unfortunately, I cannot present you any values. Actually, David got close to estimating it, but unfortunately didn't use the relative risk aversion form, but the Kara form, I think, in your experiment. And I think Sujoy is about to deliver some values, he said. And I hope to be able to give a...
Tau?
Sorry?
The tau, what is tau?
So the tau is the second order. No, it was on the previous year. We have two probability distributions now, right? We have the objective one, so theta would be the parameter of my function pi. So I don't know the growth rate. Yeah, that is probably an important point here. I assume that what we don't know is the expected growth rate. You could also assume that what you don't know is the expected is the variance of our problem, which is actually more what Weizmann did. So the simpler way to do it here is to say there is a parameter we don't know, which is the expected growth rate. And the expected growth rate is, again, normally distributed. And yeah, the prior is normally distributed over this parameter theta, which is the expected growth rate. And that's where the variance tau comes in. So forgetting about the relative ambiguity aversion for a second, the only difference we would have to the standard model is now we have actually two variances adding up here. So that was the variance we used to have earlier. That is the additional variance from the prior. That has nothing to do with ambiguity. It's simply because we now use a Bayesian model. And in the Bayesian model, we basically have two probability distributions. If each of these has a variance, we effectively increase uncertainty. So we effectively increase uncertainty here simply by putting in the prior, making our expected growth a little more uncertain. If we think about what I said in the very beginning, that the order of magnitude of these terms here is quite a bit below the order of magnitude of the pure rate of time preference and the growth expression, then that might not be a very interesting finding, simply switching to the Bayesian model, unless you actually do what Weizmann did, and that is basically assuming that you have a rather ignorant prior, and you kind of play around to make this tau go to infinity. So you get infinitely big variance, which means if you make this tau blow up here in your Bayesian model, I'm sorry, your willingness to transfer consumption into the future also becomes infinite. And then he goes ahead and somehow you have to limit it, so he cuts it off by the expected value of a statistical life. That is kind of his reasoning. I think Kanjat called it tickling infinity, which I think describes it pretty nicely. If we don't want to tickle infinity, we can rather keep everything nice, perhaps too nice. I mean, we saw that some things might be fat-tailed. But still, we take into consideration the idea of ambiguity aversion, that delivers us this additional term here, which should be red. And it's similar structure as the intertemporal risk aversion term, only that it only gives us aversion to the tau variance, that is to the variance of our prior. So with intertemporal risk aversion, you would have had the sigma here, or the complete variance of the problem. We only had sigma. With intertemporal risk aversion, with ambiguity aversion, you're only averse to, or additionally averse with this function phi to second order uncertainty, to subjective, or not subjective, to the prior, let's say. And yeah, I hope for some empirical numbers here. The conclusions are that the very standard model that is generally implied in the integrated assessment models is not a very comprehensive treatment of our attitude with respect to risk and uncertainty. There are various ways I think we should extend it, and we should extend it in a more serious way than this simple two-period idea, which just should show you that it is important. It's an important effect. And we should build it into the real integrated assessment models. And then we find that first the intertemporal risk aversion idea gives you two effects. One is you are actually more risk averse. But the other one is that because you keep apart risk aversion from your aversion to simple intertemporal fluctuations, you don't overestimate the growth term anymore in the social discount rate. And then again, we want to extend for ambiguity, which, yeah, I hope bringing some of the ideas here together today, actually, that we have different probability distributions. We don't really know which ones are the best ones. We could combine them, for example, using this model and actually try to really do a serious integrated assessment and not just such a back-of-the-envelope calculation as here. But the immediate consequences would be pay more attention to the long run and pay more attention to uncertainty. What is totally missing, I mean, there is a lot missing, obviously, but even as a back-of-the-envelope, OK, you want to combine the two, which I think pretty much my conjecture would be just adds the two term ups. I should do that. And the more interesting is probably you want to make this transfer into the future uncertain. That is, you might not be able to simply transfer a unit of consumption today with your climate action into the future. It might also be risky. Depending on what action we take, we might actually reduce the risk. So it's actually anti-correlated to the risk of our economy if we do some policy action today. It might also be correlated, and that should actually show up in this equation too, even as a back-of-the-envelope calculation. And then either analytically or definitely it automatically comes if you try to model it in an integrated assessment model. We want to have a multi-period framework with learning in particular, and I'm sure that it will actually change the numerical results quite a bit, but that is only a very start. Thank you very much.
And next, Larry Karp.
I'll try to keep this in my pocket. Okay. Well, I think that that a lot of the policy advice that economists provide is based on what Christian has called the standard model, the expectation of the present discounted value of future utility, and I think it's dissatisfaction with that model that lies behind a lot of the work that's been talked about here today, and I'm going to talk about a different way of departing from the standard model. I think there's a kind of tension between economists and climate scientists because economists gravitate naturally to thinking about discount rate or to using discount rates, and that makes us think less about the distant future, whereas of course climate scientists and the general public I think are more concerned with the distant future. So this cartoon, Scott Adams provided the preface to this talk. Dilbert's told to provide this cost-benefit analysis of an invasion, And he asks whether he should assume that hell is real or imaginary. And his boss tells him, well, assume that it's real, but use a discount rate so that it doesn't matter much. And I think that some of the climate events that we think of are a kind of hell, but if they occur in the sufficiently distant future, then with any sort of discounting, we don't care much about them. But I think that's got to be the wrong conclusion. It's a conclusion that's sort of forced on us, but it's not one that we really believe. I want to begin with two really pretty obvious observations, and I'll illustrate them, and then I'll talk about the model. Well, the first observation is that uncertainty, and I guess I should have called it risk. I come from a different background, so I don't think of the distinction. But anyhow, risk increases the amount that we'd be willing to spend to avoid a catastrophe, and that's just a consequence of Jensen's inequality. And the second observation is that even with risk, with constant discounting, if we're thinking about a low probability event, then we're still not going to be willing to spend much. And the reason is that the amount that we're willing to spend to avoid the catastrophe is to a first order approximation, it depends on the ratio between the hazard rate and the discount rate. And if we have the usual sort of discount rate, and if we have a hazard rate that corresponds to a low probability event, then that ratio is just very small, and so we're not willing to spend much. And let me illustrate those two observations with just this very simple example. The solid line shows you the stream of a flow, either utility or income, something you care about. There's a discontinuous change at time big T, and that discontinuous change represents a catastrophe. But it's possible to avoid that discontinuous change if you pay the flow X, and you think of the X as being sort of an insurance premium as a flow. And the question is, what's the maximum X that you'd be willing to pay to avoid this discontinuous drop in income when you discount at a constant rate? And I want to compare the two situations. One situation where X is just a known number, and the other situation where X is a real, where T is, big T is a known number, and the other situation where big T is the realization of a random variable that I'll take to be exponentially distributed just for ease of calculation. And this graph, on the horizontal axis, I've got the constant discount rate rho, and on the vertical axis, I've got X represented as a percentage of the value at risk. And the red graph shows you the amount, the maximum willingness to pay for different discount rates in the case where the event is random, and the solid line shows you the same in the case where big T is a known number. And of course, the point is just that you're willing to pay a lot more when it's uncertain. But this figure represents a situation where big T is chosen so that the hazard rate, remember, I'm choosing the hazard rate so that in expectation, the time of occurrence is big T. So in this example, big T is chosen so that the hazard rate is such that there's about a 40% probability of the event occurring in the next century. And I don't really think of that as being a low probability event. So I've shown the same graph, but now I've changed the hazard rate and big T so that the probability of occurrence in a century is only 5%. And you can see that if big T is certain, then you're willing to spend nothing. That's the thick line. It shows up as nothing on this graph. I mean, obviously it's positive, but it's just negligible. And the amount that you're willing to spend under uncertainty drops from around 15 or 20% to around 3 or much less than 3%. So this illustrates my point that if we're thinking about a low probability event, and if we have discount rates that are, sound kind of familiar, we don't want to spend very much. Okay, so I want to introduce hyperbolic discounting into this model because this sort of breaks the tyranny of discounting. And it provides some really important modeling flexibility that I hope I'll remember to return to later on, but I'll skip that. Okay, now most of the literature on hyperbolic discounting comes from behavioral economics, and people working in this literature are interested typically in lifetime decisions, or maybe even decisions over a decade or 15 years. And so I think that literature isn't very informative about the setting that we're interested in here, where we care about stuff that's happening over centuries. And unfortunately, or maybe fortunately, since I'm not an empiricist, there's no empirical evidence that we can appeal to think about this, and so I appeal to introspection. But luckily, I don't have to appeal to my introspection. I can appeal to Ramsey's introspection. So this is another appeal to authority, such as we saw yesterday. So Ramsey's famously quoted as saying, my picture of the world is drawn in perspective. I apply my perspective not merely to space, but also to time. Okay, but what does it mean to apply perspective with respect to space or time? Well, obviously, it carries with it the idea of discounting, because things that are farther away seem smaller, and that's what a discount rate does. But just from this quote, it isn't obvious whether perspective means that we hyperbolically discount, or we discount at a constant rate, or something else. And it's not entirely clear how to interpret a statement like this, although to me it makes a lot of sense. So the way I think about it is just to take the simplest definition of perspective that I know, and this is what architects or artists call one-point perspective. And so ignore the diagonal lines here, and just think of this as a picture of a full-on view of a railroad track that's going straight in front of you on a plane. And so the rails appear to converge, and the ties appear to be getting smaller in the distant future. Okay, so what would hyperbolic discounting mean in this context? Well, what it obviously means, I think, is that the ratio of the contiguous ties increases as we move further into the distance. And that's just because, another way of saying that is, we make less of a distinction about the distant future. We make less of a distinction about two generations that are in the distant future than we do about two generations that are close. Okay, so it turns out that one-point perspective implies hyperbolic discounting and not constant discounting. And if I had more time, or maybe I'll tell you the story at the office hour, I was doodling with this picture just as I was leaving an airplane, and a guy behind me said, I like geometry, what are you working on? And I said, oh, I know this theorem is true, and this is the theorem, but I can't quite figure out how to do it. And he said, oh, I'll send you the answer. And a couple weeks later, he sent me the proof. So it's a very simple. It's a very simple. I mean, it's just it's high school algebra, but it's kind of elegant. Okay, so I'm going to. So that's my motivation for introducing hyperbolic discounting, just because it sounds like the right way to think about the way we think about distant generations. And there are lots of different ways that you could model hyperbolic discounting. I've just chosen a convex combination of two discount factors that have constant discount rates, but there are many different ways you could do it. And never mind the numbers at this point. Okay, so now I'm going to tell you the essentials of the simplest model, the model that I think is in some respects the most informative. It's kind of similar to the earlier simple picture that I showed you before, but it's got a couple of one minor difference and one important difference, and plus it has the hyperbolic discounting rather than the constant discounting. So again, there's an event that's going to reduce income by some known fraction of income, and there's an action that I can take that costs a flow x, and I think of this as being stabilization, and the x is a fraction of the value at risk, and but in the example that I showed you before, if I undertook that action, I got rid of the risk. Okay, and that's not what's happening here. In this case, if I take the action, I stabilize the risk. That means the risk doesn't increase. And if I don't take the action, that is, if I follow business as usual, then the risk increases. So the story I have is that under business as usual, there's going to be an increasing stock of greenhouse gases, and associated with this increasing stock of greenhouse gases, there's going to be an increase in the hazard rate of this event. It's too late for me to reduce the hazard, but at least I can stop it from getting bigger. And again, I'm just picking the simplest setting I can imagine here. I've got the hazard growing at a constant rate under business as usual. Again, you could make that more complicated, but I really value parsimony, and so that's why I'm choosing this. Okay, so basically I've got this problem that involves in each period or at each instant you decide whether to follow business as usual and allow the hazard to increase, or you decide whether to stabilize, incur a cost, and have the hazard not increase during that period. But because of hyperbolic discounting, we have a time consistency problem arises, so they're really different equilibrium concepts. So the least interesting one is unrestricted commitment. The guy today decides on the entire trajectory of future decisions. That's not interesting. I won't talk about that anymore. Although actually there are a couple of papers that use hyperbolic discounting, a couple of papers not written by me that use hyperbolic discounting in climate settings, and they do use this unrestricted commitment. Maybe they were the referees for my paper, right? I don't know. But there's another equilibrium concept which is only interesting as a baseline. I call that restricted commitment, and this is the idea that the regulator can't decide on the entire. The regulator can't decide at the point in the future at which to stabilize. He can only decide whether to stabilize today for infinity or to never stabilize for infinity. So that's obviously a very strong kind of restriction. But I think the most plausible one to people who think of these sorts of differential games is to look at a subgame perfect equilibrium, or rather a Markov perfect equilibrium, which is subgame perfect. And I haven't said it before, but those of you who are familiar with this sort of setting will know that the standard way of thinking about this is in a subgame. If you're interested in a subgame perfect equilibrium, is to model it as a game amongst a succession of generations. Each generation has the same objective, but the guy today can only choose what he does today, and in doing that he affects the state that his successor inherits, and in this case the state is just the level of h, the hazard. Okay, so I'm interested in the Markov perfect equilibrium, and I've just described it here, and it turns out that this problem is not as horrific as it might seem. Those of you who are familiar with this sort of optimization problem, well, if you just forget about this function k, everything else is just exactly the dynamic programming equation that you would get for the model with constant discounting. But the presence of hyperbolic discounting and the need to consider this Markov perfection introduces this additional function k, and it's defined here. And so that makes the problem a little bit more difficult. Let's see. And I guess here I'll put in my plug for simple models. I mean, this is a really simple model. I've got a utility function, and I use for most of the example I use the Kara utility function, so it's a one-parameter function. I've got a constant growth rate in business as usual consumption. I've got the magnitude of the catastrophe represented as a percentage of loss in income. I've got x, the cost of stabilization, as a fraction of the magnitude of the hazard rate, and then I've got three parameters that describe the level of risk, the initial value of the hazard, and then the two parameters in the growth equation for hazard. And I really think, you know, if you look at what we know about climate change, it seems to me that a model this simple, I mean, obviously I'm biased, but it seems to me that a model this simple is as compelling as the integrated assessment models that are much more commonly used. And of course, the advantage of a model this simple is that you can complicate it in other dimensions, in this case by thinking about more interesting types of discounting. And I'll just mention that these integrated assessment models are really puzzling to outsiders and even to insiders. The DICE is, I think, one of the most carefully documented integrated assessment models there is, but there's a lot that's mysterious about that too. And there's I think, a great paper by Rezai and Duncan and Foley coming out in economic theory that explores some of the issues of the DICE model, and I recommend that paper. Okay, so as is very common in models of this sort, and now I'm just talking about the Markov perfect equilibrium, as is common in models of this sort, you have multiplicity of equilibria. And basically the reason you have multiplicity of Markov perfect equilibria is because the thing that's optimal to do today depends on what I think people are going to do in the future, because what I think people are going to do in the future affects the shadow value of the state variable, and the shadow value of the state variable affects what's optimal for me to do today. So you've got this sort of non-uniqueness, and you can really characterize the non-uniqueness very clearly, very completely. But it's, I won't say more about that. And I'll just, except for one comment, I can compare, all right, I'll say a little bit more. The Markov perfect equilibria, there are a bunch of different types of Markov perfect equilibria. So for a given initial condition and a given set of parameters, I might want to stabilize beginning now, or I might never want to stabilize, or I might want to wait for a while and stabilize later. Okay, so there's kind of a rich set there, and I can, but there are typically going to be these two Markov perfect equilibria. I stabilize now, or I never stabilize. And remember, those are the only two choices in what I call the restricted commitment scenario. And so the restricted commitment scenario, it provides kind of a natural way of a baseline against which to compare the Markov perfect equilibria. And the point I want to make is just the final point there, which is that stabilization in Markov perfect equilibrium might be either excessive or insufficient relative to the restricted commitment. Okay, so I want to close with an example. And I've just given you some of the parametric assumptions. And actually, I realize this is an old slide. The paper has somewhat different parametric assumptions, but the assumptions, the results are not significantly changed. So I've chosen the initial hazard rate and the parameters of the growth rate for the hazard, so that under business as usual, there's about a 15% probability of the catastrophe, and under stabilization today, there's about a 1% probability of the catastrophe. And then I chose a number of different values for the magnitude of the catastrophe, representing maybe 5% or 10% or 20% of gross world product in the future. And then I've chosen some parameters of the discounting function. And I also have a growth rate floating around in there, but that just makes things more complicated. And I guess all I want to say is that I'm not going to talk about these specific numbers, but I'll just say that I don't have to stand on my head to come up with reasonable assumptions that give policy conclusions that are very similar to those in the Stern report. and so I mean, I think that that's a reason for, maybe that's another reason for thinking that some of the criticisms leveled against the Stern report are maybe not so compelling. So the other point I wanted to make about this is that because this is such a simple model, I can pick a Markov perfect equilibrium. So for example, I can say what is the level of x, that is the cost of stabilization. What's the maximum cost of stabilization for which there is a Markov perfect equilibrium that involves immediate stabilization? And then I can also say what's the minimal cost of stabilization for which there's a Markov perfect equilibrium that involves, or such that for cost below that level, all Markov perfect equilibria involve stabilization. And so, in other words, I can select the Markov perfect equilibria that are on the bounds of that are on the boundaries of the set of equilibria, and then I can say, and then I can ask, what would be a constant discount rate that would lead to the same decision, and you know, in general, with models with hyperbolic discounting, there's not a constant equivalent discount rate. I mean, there are in very special settings, but not in general. But in this case, there is a constant equivalent discount rate. And again, I end up with numbers that seem pretty similar to the levels that Christian reported that Stern used. So I think that his assumptions are not, you know, they're defensible on these grounds. Okay, so I guess I'm about ready to conclude that, you know, I think that most climate change problems really require taking seriously what happens in the distant future, and it's kind of hard to do that if we also insist on fitting a social discount rate to market rates, such as Nordhaus does. But it seems to me not so reasonable to want to do that. I mean, you know, it seems reasonable to fit market rates to discount rates in the near run, but if we're thinking about discount rates for 100 years from now or 200 years from now, why should we be interested in the market discount rate? It doesn't seem like it provides much evidence on how we feel about, it doesn't seem like the market discount rate provides much evidence about how we feel about the trade-off between distant generations, unless you think that the pure rate of time preference is a constant, in which case you don't have any of the time inconsistency problems, and in that case you can justify that procedure. Okay, so this model, you know, this model makes it possible to evaluate climate change policies using different assumptions, and I guess I'll just say again, this is a real simple model, and I can get everything in closed form. I mean, the expressions are pretty ugly, but it's just very transparent, and I think that that's a virtue not shared by a lot of the models that are used to make policy.
Thank you. And now we have as discussant Ralph Winkler.
I don't know how to get out of there. I'll leave it to someone technically more sound.
Thank you. It's my great pleasure to serve as a discussant for Christian's and Larry's presentations. Actually, when I thought, how shall I structure my discussion, I thought it might be not that useful to you that I really pry into the details of all these models. Instead, what I want to do in the next 10 minutes is that I rather want to reflect the lessons I learned from reading these two papers. But let me
very briefly summarize what Christian and also what Larry presented here. So Christian's point was that the standard model implies intertemporal risk neutrality, and apart from David, nobody here in the room seems to be intertemporal risk neutral. So this is really, no offense, it's just mean, I just wanted to say it seems he has a real point here that intertemporal risk aversion is something which you really find. And risk is insignificant for certainty equivalent social discount rates in the standard model, but it is not. It is not if you take into account intertemporal risk aversion, and with some very easy back of the envelope calculations, he showed that you easily come up with numbers which reduce social discount rates significantly, so that you more or less you can compensate for the growth effect. So the discount rate more or less comes down to the pure rate of time preference in essence. And it might be, we don't have numbers yet, but it might be that ambiguity aversion might have a similar effect. And in fact, if you perceive climate change as a situation where you have both, where you have intertemporal risk aversion and where you have ambiguity as well, this might add up to some extent. Of course, this hasn't been done yet, but it was promised to be done in the future. But actually, I think it's quite likely that the combination will be either lower than adding up. The paper presented by Larry was, of course, somewhat different. So what we've seen there was we have a succession of hyperbolically counting agents which can invest in abatement. And what abatement actually does is that it reduces the probability of a catastrophic climate event, which just depends on the stock of greenhouse gases. So actually, what I really liked in this paper was what we also find out yesterday in the discussion, that what we do if we do climate policy, it's not that let's say, we have a deterministic outcome if we apply climate policy, but what we actually buy by mitigating climate change is we buy a damage probability distribution. And this is exactly what is modeled here. Depending on how much we abate, the less likely is it that we have a catastrophic event. Larry does some reductions to let's say, to come up with a very parsimonious model, as he claimed it. So we only have a business as usual versus a full stabilization scenario. In general, and this is quite common for this literature, we have a multiplicity of Markov perfect equilibria, and this still holds, although we have this very, very restricted set of possible actions. And also, which is not that uncommon in this literature, is that the market perfect equilibrium might be inefficient compared to a commitment case, so that we might either have too much or too little abatement. And as Larry also pointed out, he can calibrate his model very easily to come up with numbers that are quite similar to what the Stern report says. And perhaps he just mentioned constant equivalent discount rates that he can compute, and they are in the range between 0.1 and 1.8%. So this is very much in between. So 0.1% was the Stern pure rate of time preference, 1.5 was the Nordhaus pure rate of time preference. Of course, there were different assumptions, different scenarios with different intertemporal elasticities of some substitution and also different growth rates. But of course, this is a range which sounds very reasonable, no doubt about that. The first thing which really struck me when I read Christian's paper was that in general, what we have a perception about the social discount rate and what it tells us in climate change economics. So, and this was very well highlighted also by the Stern-Nordhaus debate. If we have a high social discount rate, this means we have a low optimal carbon tax, and therefore it is not efficient. It's not efficient to, or it's not optimal to really mitigate a lot of CO2 emissions. And of course, to some extent, this was also true in the setting presented by Christian. So if it just said if we have uncertainty, then the discount rate becomes a little bit less. But of course, if the discount rate becomes less, then this also means we are inclined to abate more. But as as we have seen, as we've discussed yesterday quite a lot, and which was also the case in Larry's paper, that climate policy is rather a choice between different damage distribution functions, and it's not so much about, let's say, how much consumption can I put forward into the future. And if climate change mitigation is rather like I change this probability function, so I change these uncertainties, it might very well be that a strong climate mitigation policy might increase my social discount rate. So if you, for example, think about a policy which either, let's say, increases the growth rate, the uncertain growth rate, or which reduces the standard deviation of the distribution. So it reduces the volatility of the growth rate. And what this means is that the equivalent, the certainty equivalent social discount rate becomes higher. So this seems like some kind of a paradox. I think the reason why this is what we actually do is we implicitly change from an exogenous growth integrated assessment model, which we are used to see, the Stern, the Nordhaus integrated assessment model, they were all essentially exogenous growth models, to an endogenous growth model. Because what does our climate change policy actually do? It allows us to change the growth rate. And of course, if the growth rate increases, that means it is more valuable for us to invest in capital, because the social discount rate is not just the rate at which we trade off consumption. It is also our rate of return to investments in capital. And so I think the bottom line to take away is that don't get too obsessed with social discount rates. If we make our models a little bit more complicated, if we account for uncertainty, if we account for ambiguity, what we actually do is we switch from an exogenous growth model to an endogenous growth model. And then what matters is rather looking really at the optimal climate change policies, and not so much about what is the social discount rate it implies. That was the first point I'd like to make. The other one was that when I read Larry's paper, more or less the conclusion was that catastrophic climate events might, let's say, might incline us to mitigate more CO2 emissions than perhaps put forward by models like Nordhaus. But it is not that we, let's say, that we give our last shirt for avoiding a catastrophic event. And it struck me because in the last 2 years I heard at least 2 presentations which had a little bit different conclusion. And one was by Amos Zemel and Jakov Zur, and another one was by Eric Neftal. And actually they more or less come up with the conclusion, if you have a real catastrophic event, discounting is more or less a second-order issue. I'm quite sure that Larry got it right, and the reason why is that if we look at what does catastrophic event mean with respect to climate change, it is not that catastrophic event is a meteorite which is endangering humankind as a whole. And of course, if catastrophic risk is such that it is really lethal to all of us, we might really be inclined to sacrifice a lot. But this is not really the way catastrophic risk is with respect to climate change. With respect to climate change, of course there are similarities. Catastrophic risk means we don't see much of damage until a certain threshold. Then we get a discontinuous jump in damages, and there is some irreversibility that we can't easily go back, or perhaps we can't go back at all. Nevertheless, I think what is really different about catastrophic risk with respect to climate change is that catastrophic damages are very heterogeneously distributed. Think, for example, about the melting of the Greenland ice shield. Of course, for Greenland, it might have even positive effects. So you gain access to a lot of land, which is more or less unusable because it's covered by ice today. Then, of course, there is some sea level rise, which you will have from all this ice melting and dropping into the sea. I don't know the exact numbers, but it may be something like up to 10 meters or something like that. Of course, 10 meters might be a lot. Sea level rise of 10 meters really affects you if you live here in the Bay Area. But it doesn't affect you at all if you live in Switzerland. You don't care. So it very much depends where you live. Sorry? Yeah, we're very much in the middle of Europe. We really hope that the European borders are close enough that they don't want to make it to us. So actually, what I think catastrophic damages or catastrophic risk might perhaps not so much be might be a problem for the intertemporal dimension of climate change. But what I want to say is that also yesterday and also today is we talked a lot about this intertemporal dimension, but we overlooked a little bit that there is an intergenerational collective action problem as well. And it might be that particularly catastrophic damages might be more of an issue if you think about international climate change agreement negotiations than it is for the intertemporal problem of discounting and so on. And also, I think uncertainty ambiguity might really have a punch with respect to climate change negotiations. Paolo said that one of the reasons why there is so much work on ambiguity is that we want to capture that different people have different levels of ambiguity aversion or different attitudes to ambiguity in general. And in particular, if you think there is some kind of a level effect, the more wealthy you are, I don't know really in what direction this might change your ambiguity aversion, but simply say that it might change your ambiguity attitude, then this might, of course, be relevant for climate change negotiations as well. In particular, if you think about, and now I come back to my previous point, in particular, if you think that policies, climate change policies, are rather changing damage function distributions, depending on your particular attitude to risk and uncertainty, you might promote different climate change policies which render you different kind of damage distribution functions. So my last sentence is don't forget the intragenerational collective action problem, although I of course credit that also the intertemporal problem is very relevant.
Thank you. We have 15 minutes or so for questions and comments. The three of you should say.
Right. I got a comment which probably applies to both papers by Larry and by Christine, and to a large extent supports what the discussant was talking about. And that is, in all of these models, when we talk about time preference rate, we forget that conceptually it may not be applicable to the problem of global warming when we are talking about hundreds of years or at least 100 years of differences between generations. Conceptually, in economics, we know that time preference rate measures trade-off in consumption between 2 points in time incurring to the same individual. In other words, we are holding the utility function as representation of the preferences to be the same between the 2 points, and then look at the trade-off. Whereas here, we are talking about totally two different generations. One is the one who has to incur the abatement costs, and the other is the one who would basically receive the transfers in terms of reduced damage. And these two, being at least on the time scale of global warming apart from each other, don't have the same preferences, and therefore it really makes the concept of time preference rate ambiguous in terms of its application to this particular context. And therefore, I think it may lead, this argument, if it's valid, may really give weight to what the discussant was saying, that we shouldn't really hang up so much on the time preference rate, and of course its translation to social discount rate, than looking at actually policies which are optimal in terms of transfer of resources to future generations to enable them to cope with climate change.
Yeah, probably we should first define what we mean by time preference. You were talking about individual time preference. I think there are definitely both of these out. There is the individual time preference and the intergenerational time preference. I think, for example, Stern actually pretty clearly argues for an intergenerational rate of time preference, while Nordhaus kind of mixes the two up in his paper. I think like he goes and estimates kind of the individual one, but then he talks about the intergenerational one. So it's a little bit hard to disentangle them, and I might advertise a paper that actually we are just writing where we kind of look at the two different ones in the same model. So we have an overlapping generations model for the individuals, where everybody has his own trade-offs over time and his own individual pure rate of time preference. And on top, we actually put a social planner who has his rate of time preference, which would be the intergenerational rate of time preference. And so yeah, I think it is very important to disentangle them, and there are actually pretty interesting results if you try to do so. I wouldn't say that for that reason you just like shouldn't do it and you shouldn't look at it. You should just look at it probably more comprehensively. I would actually think that in Larry's model it was to be understood as the intergenerational rate of time preference, but probably Larry might want to correct me. In my situation, it was really just a simple back of the envelope calculation where I looked at it as if we would have a representative consumer, which we generally don't have, but to get like a first idea before getting into complicated, more realistic models.
Well, most of these models are representative, agent or generation models. So to that extent, the preferences remain the same. So evaluations of the consumption at different points in time evaluated based on the same preferences. What I'm talking about is a different thing. In fact, in overlapping generations, and the model that Larry was talking about too, the preferences remain the same, although the decision-making, namely what one generation inherits from the past generation's decision, could affect their decision as to how much to invest, let's say, in abatement and how much to consume. But the point is, what I'm talking about is changes in preferences between current generation, who has to take the cost of abatement, versus preferences of future generations, which are totally different. So it's not just a matter of either representative consumer or overlapping generation in the models that we have got with the same preferences, but weighted differently.
Sorry, one very quick comment on it. I think, yes, I mean, we assume, I would naturally assume stationarity of the preferences, because we cannot say anything better. If you have like a better model that actually predicts you precisely how preferences develop over time, we could take it into consideration. But if we just say we don't know anything, one extension would be to use like a preference for flexibility type of framework. But
well, this relates to the theme of the conference, that ambiguity could be also applied to our not knowing exactly the distribution of preferences of the future generation.
Yeah.
It's, in the context of these models, I'm not familiar with this literature, but does anybody look at the implications of having an operant intergenerational bequest motive in these models, which would then change this discussion quite a bit, actually?
Yeah, actually, I think what Nordhaus and Stern implicitly, Stern less because it's rather normative, but what Nordhaus implicitly assumes is that you have some kind of a Barrow equivalence, so that you really have an operative bequest. And this is to some extent a justification to use a Ramsey-type consumer as a social planner. If this is really justified, this is a very interesting question, and this is also part of the question Christian, me, and one of our colleagues, Mike Schneider, is analyzing in the model Christian just briefly talked about.
Because in fact, in the economy, people are making intergenerational transfers.
Yeah, this is debatable. There is quite good empirical evidence that that there is no really operative bequest motive. That you give more because of a feeling of a warm glow than real altruism. And there is another point that there might be a real difference whether you inherit a portfolio of stocks. Mm-hmm. Or if you leave your children a better nature. So I think there is a strong complementarity between natural capital and man-made capital. And of course, what just looking at the real rate return on capital does is it completely neglects that there might be some complementarity. Mm-hmm.
I'm going to come at this with, I think, a sort of a different model, and then the question is whether this is orthogonal or to what extent it overlaps with what you guys have been saying. But I run a little center at RAND on long-term policy analysis, and so the question you always get asked is what difference does that make? Does decision makers ever think long-term? And so we've, in a very non-scientific way up to this point, kind of gone through and tried to identify examples where decision makers do think long-term. And the general characteristic, roughly, seems to be, if you have a sense that, and thinking long-term is you do something different today because you're thinking about potential consequences long-term, way in the future. And sort of the general characteristics is people seem to think, real life decision makers seem to make long-term decisions and make real sacrifices when they have plausible reason to believe what they do now actually has some effect many generations from now. Sort of that there's some reason to believe you have action at a distance. And so that often occurs when you get to write constitutions, okay? It kind of occurs when you get to pour, concrete and build cities that you think are going to be around for a while. And, just to kind of, two little quirky examples, the historian James McPherson has this wonderful book called Why They Fought, which is essentially extracting out why did the Union and Confederate, soldiers actually sit there in the mud and get shot at based on letters to their wives and girlfriends and families. And his conclusion is essentially they really believed that they had two different views of freedom, but what they were really doing was good for the freedom of mankind. On the other hand, Sherman marched through Georgia and basically did his best to reduce consumption and capital to zero, which he basically succeeded in. And today, the average income of Georgia is where it was before. So, on the consumption side, after 150 years, what happened in 1864 made no difference. But one could argue that the privates were actually right. It was that getting shot at actually made a huge difference into the political, in the normative and political structure of the world, and they kind of got it right. So is this notion that you think long term, sort of independent of discount rate, when you have a real reason to believe what I do today will have enduring consequences, that people 100, 200, 300 years from now will actually understand that what I did today made a difference, but in most cases, what I do today makes virtually no difference on what's going to happen more than 10 or 20 years from now. So is that consistent with your model, different? How would you think about that?
Yeah, I think it's consistent. I mean, the sort of the nub of the question is how are you going to aggregate this difference over a very long time span, and even if the difference is significant, the fact that it begins only in the distant future may cause you to regard it as negligible. So you've got to think about both of those things: how you aggregate the change that once it's occurred over from then until infinity, and then how you bring that back to today.
I think of that in a multi-attribute sense. How much am I willing to trade to have the enduring influence?
Yeah, I find the debate, the Nordhaus-Stern debate, really frustrating because it seems to me Nordhaus has got away with a straightforward factual error that then confused the entire debate. That is, he says he's describing the market rate of return, but what he's using is a market rate of return to risky assets, when the model clearly says what he should be using is the riskless rate, which is the bond rate, which is almost exactly what Stern has. And everything, really, I think Christian's sort of gone backwards. I mean, to resolve the problem, one way of fixing the problem is to use Epstein in. They explain why the gap between the bond rate and the equity rate is so much larger than it ought to be. And by putting that back into the model, you end up back at Stern where you should have started, because everybody's willing to accept, for no reason I can understand, that Nordhaus has a descriptive approach, when he doesn't. We have just a straightforward error that has got the debate wrong from the beginning. And I guess going on from that, once you buy the Stern story, your delta, the pure rate, has to be very low. It has to be dominated by the kind of all bets are off. There can't be any big room for any pure rate of time preference in the ordinary sense of the term. It has to all be stuff like, look, really, when we say 150 years' time, we've heard from the scientists, but we don't really know. For all we know, even now, the investments we make might be totally worthless. We might discover some simple cure in 50 years' time that wipes out the problem, or we might blow ourselves up, or something of that kind. And the delta has to be pretty small, so it has to be dominated by those kind of factors. And then come into things like the bequest motive. The observed rate of growth says we must be bequeathing to our descendants, not primarily through what we leave them in our wills, but collectively through education and stuff like that, and technology, enough that they experience a rising standard of living, which is what then gives you the discount rate. And all of that means that if you know there's going to be a catastrophe in 100 years' time, you shouldn't be discounting it at all. The only reason we discount catastrophes is because we don't really believe in them. So.
I agree.
Well, okay, I pretty much agree, but not entirely. I mean, I think I think it's a bit of an exaggeration to say that Nordhaus has just made a mistake. I think that there is a rationale for the exercise that he carries out, but I have the criticisms about it that I made. So I don't think it's quite as stark as you pointed. But
I just wanted to come back a little bit more to the stochastic aspects of both, particularly Christian's model. So in a sense, if you take a more finance perspective, because really you're separating out intertemporal substitution and risk aversion, also allows you to get a handle on the equity premium puzzle. So I have two questions. The first question is, presumably it matters a lot whether the investments you do to mitigate climate, how they are correlated with growth in the very long run. Because if this, let's call it investment climate beta, or whatever you want to call it, is very positive, is very strong, you have a very high rate of interest or very high discount rate, you're not going to take much action. Vice versa, if it's more like a UNESCO property, which doesn't affect the economy very much, but it's just very beautiful, the interest rate you would use would be rather smaller, and you might be engaged to kind of take more vigorous action. So that's not in your model. So that's one question. And the second part is a bit related to the current crisis. So sorry for being very pragmatic or very... if I were a journalist, I would ask the question, well, we just had an enormous global financial crisis. We just had an enormous financial global crisis where maybe people start to rethink this equity premium puzzle, that maybe there may not be any puzzle in the long run. I'm not sure whether that's true or not. Do you have any thoughts on that, or is that all too pragmatic?
The first point about the beta, was exactly what I kind of meant when I had that up the board. And Ralph actually mentioned it too, that even for a back-of-the-envelope calculation, probably that you want to extend it to the idea that actually you don't have like a certain investment project, but actually the interesting thing is what Larry partly model, how you change the probabilities. And I would say if it's like anti-correlated by basically reducing the risk with my climate action that I take, which I think would be the reasonable assumption if we think that we're currently perturbing our climate system quite a bit. And if we perturb it a little bit less, we know at least like a little bit more about what is going on, then our action might actually be anti-correlated, at least to that part of the baseline risk, which is kind of the risk that the climate produces. Then it would probably increase the effect. On the other hand, if the action would be totally correlated to the overall economy, growth uncertainty, I totally agree. It would be lower, would make less of an effect. So the discount rate would stay higher. No, I don't have any. So that would be the next. I mean, really just putting in the correlation term there. But then where to get the quantitative estimates for the correlation is actually a very good question, and I wouldn't know from the tip of my head. But perhaps if anybody would have an idea, I would be really interested. Well, yeah, that's a very good point.
I mean, you just try out different parameters. I mean, you can't calibrate it because I don't know the data. It seems to have a huge effect.
Yeah, it will. So I mean, the least thing I could do is like look at a beta and look at different values. But to calibrating, it seems. I mean, once we want to integrate that whole thing into a dynamic integrated assessment model or something like that. You should probably try to calibrate the whole model and then calibrate the beta somehow too. But that's way beyond what the back of the envelope calculation here. The second one, the financial crisis and might the equity premium puzzle be gone? Well, probably an easy answer would be everybody raised his hand here when I ask. Despite financial crisis and everything, people seem to be intertemporally risk averse, except for you actually. So, but I don't know. I mean, right, definitely there is some intuition that there might have been this fat tail out that we didn't take into consideration when we estimated these models in 2003, like Wissen, Jurgensen, and Atanasio did. But
Could I comment just a tiny bit on beta? I mean, if we look at the moderate damage scenarios, all the damage occurs essentially in agriculture and natural environment. And so you can pretty safely say beta is zero. That the correlation between food prices and returns to equity is pretty low, and the correlation between the natural environment and returns to equity is pretty much zero. And if you look at the catastrophic damage case where climate is the dominant risk, then I guess you're going to have a negative number. So I mean, depending on, it has to be, I mean, the risk adjustment has to be either zero or negative, whereas, as I say again, Nordhaus implicitly is assuming that that beta is something like 1. And that just seems to me to be, the fact I continue to be stunned that he gets away with calling this a descriptive, claiming as a descriptive fact around the world about the world that there are riskless investments that return the average rate of return to equity, the average rate of return to capital, when the whole point of that average rate of return is that it has this huge risk premium in it.
I have a question for both of them. One of the most relevant critics to Stern approach is a Weizmann approach with respect to discount rate. But in your opinion, the critic of Weizmann is related to his view of the opportunity set, in the sense that, in his view, in the famous article related to the Noir problem, he has a view of the opportunity set measured by the chain. That is, he has a phylogenetic approach in which what is relevant is the change that you have in the opportunity set. But if you does not accept this approach, and you measure the opportunity set, the diversity in the opportunity set in a different way, probably his critics in terms of discount rate has a different value. For example, the intertemporal discount rate or intergenerational is irrelevant, but there are a lot of seminal paper of Jeff, for example, in which if you fix some part of some level, some threshold in the opportunity set, your solution are bounded, of course, and you can take into account of intergenerational preference, for example.
So I'm not sure I entirely understood the question, but I'll take it as an opportunity to comment on Weizmann's criticism. I think that I think that the interpretation that he gives and that others have given to his results are just fundamentally wrong. And there are a couple of criticisms of it. In my view, the most important, or at least maybe the most obvious, was really clearly made in a paper that Andreas and John Horowitz wrote, and that's that Weitzman, even if you are willing to accept that you can transfer a sure unit of consumption into the future, Weitzman is looking at the discount rate associated with the first with the first unit that you transfer, and the fact that that discount factor turns out to be infinity in his setting just means that you don't have a boundary solution. It just means that you want to transfer, if that transfer were possible, that you want to transfer a strictly positive amount. And if you consider it in an optimization framework, then it becomes clear that even though at the boundary this thing that he calls the discount factor, the marginal utility of income, and the present value of the present value of the first sure unit of income that you transfer, even though that in expectation may be infinite, that doesn't really vitiate the use of cost-benefit analysis. And just one further point to that, Nordhaus criticizes, he has an interesting criticism that goes along similar lines, although I don't think he makes the point as clearly as Andreas and Horowitz did. But interestingly, although most of Nordhaus's argument goes to objecting to Weitzman's conclusion that you can't do sensible cost-benefit analysis with fat tails, even though that's the basic point he wants to make, he goes on to agree with Weitzman that the inclusion of fat tails renders the discount factor, or the discount rate, a second order feature. So, and in fact, that conclusion is wrong, or at least it's wrong in general, for exactly the same reason that Weitzman's conclusion is wrong. I don't have time to explore that point further here, but one of the sections in the second paper that is online that I didn't talk about today looks at exactly that issue. And so my conclusion is that fat tails doesn't render cost-benefit analysis nonsensical, and it also doesn't necessarily render the discount rate to be of second-order importance. And those are for exactly the same reason. So sorry for the long answer before lunch. But
well, we'll have lunch and reconvene at 1:30, and lunch is outside.